Hello class. This first video is going to be the first in a set of two videos that is going to cover the material that we've done in this unit. So it's going to be an overview. We're not going to go into a lot of detail, but just to kind of jog your memory, remember the things we were talking about, what everything meant. So this video is going to have 6 main parts, and it's going to be just a general overview of waves. So we're not going to get into any specifics about differences and similarities between light rays and sound rays and other sorts of waves that we've talked about. So this one is, you're going to start with different types of waves, the 2 different types of waves we've talked about, then talk about the equations that apply to waves. Then we're going to talk about interference, reflection, refraction, and diffraction. And all of these are things that will apply to all waves and are not specific to any one type of wave. Let's get started. So first we're going to talk about the 2 main overview types of waves that we talked about. So the first one is going to be the transverse wave. This is the one that's going to be represented like a sine wave that you've become fairly familiar to. We talked about this when we did simple harmonic motion and that sort of thing. Now remember, the motion of a transverse wave is going to be perpendicular to the displacement of the particles. So while the wave moves up and down, while the particles move up and down, the wave is going to move forward. Remember, we have specific spots that we want to keep track of. We have here the peaks, and then below we have the troughs. And remember, in order to get what the wavelength of this wave is going to be, we have to either go peak to peak or trough to trough to figure out the wavelength. We use this lambda symbol to talk about the wavelength. So if we were going to then talk about our other type of wave, we have what are called longitudinal waves. Remember, for longitudinal waves, we also have special words when we're talking about the different parts of it. So we have here compressions. This is where all of our particles are going to be getting really close together, pushed together, compressed together. And then over here we have rarefactions, which is where they all spread back out. Rarefactions. I don't think there's an R in there. Rarefactions, yes. And again, we don't figure out the wavelength with peak to peak or trough to trough because we don't have peaks and troughs, but from rarefaction to rarefaction or from compression to compression, that's going to give us our wavelength, again marked with the lambda. Remember that the motion of the particles back and forth is going to be parallel with the overall motion of the waves. So even though the particles may be compressing back and forth to the left and the right, or refracting back and forth left and right, the overall wave moves from left to right, and so they're parallel with each other. Now I know I titled this section Equations, and that's kind of true, but kind of not. There are going to be other equations that are probably a good idea for you to know that you may need to reference, but these 2 that I'm going to talk about in this section are really the most important ones. So we start off with our just good old kinematics equation dealing with distance and rate. So the rate at which something moves is the distance that they move in a certain amount of time, so distance divided by time. So in physics terms, we have our velocity is equal to our displacement divided by our time. Sometimes this is written as v equals x over t. People will use other variables for that x there or the d, but it basically just means whatever distance we're traveling and however much divided by however long it takes to travel that distance, that gives us the velocity something is moving. Now, typically when we think of this equation, we think of like a ball being thrown or something physical moving, but in the terms of waves, this same equation occurs. It still applies. We have a distance, either x or d, is going to be equal to the divided by the time is going to be equal to the velocity that that object is moving. The other equation that we have was about wavelength and frequency. So we know that our velocity is equal to our wavelength times our frequency. Now I guess we should go in and talk about units. Over here our distance is in meters, our time is in seconds, our velocity is in meters per second, so units check out there. What about over here on the right hand side? Our wavelength is going to be in meters, our frequency is going to be in hertz, but remember hertz also means 1 over second. So if we take meters times 1 over second, we get meters per second, which is what we would expect to get for a velocity. So we have our two equations. Velocity is equal to distance divided by time, and velocity is equal to frequency times our wavelength. Now we need to talk a little bit about interference. Now, we had two different scenarios in which we talked about interference. The first is when you have two wave pulses that are approaching each other and meeting each other at the same location. So if we have a square coming in from the left, and then from the right we have some sort of triangle thing. If this is coming from the left, this is coming from the right, when they meet together, they're going to make a little house. Because they are both positive, they're going to stack on top of each other and create a house. Now, this, you can also look at what's going to happen when we have two things that are not facing the same direction. So that was two positive, but what if we erase that and make it two negative? So, or a negative and a positive. So we have a negative square, a positive triangle. When they meet together, we'll end up with a negative square with a triangle kind of bit out of it. So because this square from the left is negative, this from the right is positive, then they're going to cancel out, and what we're going to be left with is this subtracted from this, or this minus this, or this shape pulled out of this one, which is what we get. So this is how we deal with interference when we're talking about waves. But this is just for an individual pulse. So we also talked about the scenario of when we have two speakers. Remember, we had a speaker over here on the left and a speaker on the right, and we were trying to figure out our little concert goer over here, what they are experiencing and hearing. And it all depends on the distance between the speakers. So if the distance from this speaker to our concert goer is 3 wavelengths, and the distance from this one is 5 wavelengths, then that gives us a difference of 2 wavelengths. 5 minus 3 is equal to 2 wavelengths. Because this is a positive whole number, so if we end up with whole numbers, we get constructive interference. That means that they're going to build together to make the sound louder. So this is constructive. And then if we get a half wavelength, so let's say instead of 5 wavelengths, this other one was, let's say it was 4.5 instead of just 5, 4.5 wavelengths, then we would have 4.5 minus 3, which would end up with 1.5 wavelengths. And because this is a half wavelength, this is going to be destructive interference. So let me rewrite that so it's actually legible. So when we say a destructive interference, what we really mean is that somebody sitting in that spot, 3 wavelengths away from one speaker, 4.5 wavelengths away from the other one, is not going to hear any sound. That's because we're having destructive interference. All of the waves cancel out. So whole wavelength, we have constructive. Half wavelength, we have destructive. So now we need to talk a little bit about our first property of waves, reflection. Well, I guess we talked about interference, so that's a property of waves. So our second property of waves, reflection. So the first thing we want to look at is how do we see this image of the star reflected? So remember that with the law of reflections, the angle that a light ray approaches and becomes incident with a mirror is going to be the same angle as it is released. So these angles are always with respect to the normal. So we're going to say that this angle right here, theta, has to be equal to this same angle right here. Theta is going to equal theta. So with that, we can also look at how this image is going to be seen by an observer. So first, we got to move the image to be in the location that we would think that it's going to be seen on a mirror. Now remember, the distance from an object to the mirror is going to be the same as the distance from the mirror to the image. So what we have over here on the right is the object. This is the actual physical, tangible thing we can see in real life. And this on the left is the image. This is what we think we see in the mirror. So it's going to go over here on the left-hand side of the mirror, and the distance between our object and our mirror is going to be the same. Okay, suspend your disbelief, call this the same distance between our image and our mirror. So if we're looking and we have an observer over here on the right where this ray ends up, just chilling, our observer, we want to see how he sees this image. Because he sees the image and doesn't really realize about the object, we say that he has a line of sight from the observer to the image. And we see that's going to be right here following this path. At this point where it intersects with the mirror, let's draw this line better. At this point here, where it intersects with the mirror, that's where the properties of the mirror and the law of reflection take over. So we intersect with the mirror, and that means that that's where our observer sees the light rays coming from, but we know because of the mirror that it's going to bounce back. So they think they see this image here on the left, they're really seeing the light ray coming from the object, bouncing off the mirror, and going to our observer. Because this perceived line of sight with the image takes us through the mirror, this means that our observer can actually see this object's reflection. So we also talked about other types of mirrors besides plane mirrors, specifically concave and convex mirrors. Remember, concave are mirrors that are going to focus the light inwards. So parallel lines of light are going to come in, bounce off, and be focused towards the middle. Convex mirrors, on the other hand, are going to scatter the light. So the light comes in, reflects off, and goes in all sorts of other directions. So these are the types of mirrors we talked about. Plane mirrors, how to get these images and reflections, whatnot, and then convex and concave. Refraction is the bending of waves as they pass from one medium or one material that they're traveling through to another material. Now specifically, we talk a lot about refraction for light rays, but it does occur with sound waves. But light rays are where we see it the most readily. So remember, when we have light coming in from one medium, it hits this barrier and it's either going to bend away or towards the normal. So our normal is the line perpendicular with our surface, and so here, if we're going from an n of, let's say we're going to an n of 2, we came from an n of 1.5. This is increasing our n value, and when we increase our n value, we move our line closer to the medium. So we start with this wide angle, and this angle here between our normal and our ray is going to get smaller as we get into the other material that we're traveling through, because we're going from a low index of refraction to a high index of refraction. Now remember, we talked specifically about an equation we could use to figure out these relative indices of refraction and to figure out what these angles are going to look like. So if we have our sine of our theta incident times the n of our incident material, this is going to be equal to sine of theta refracted times n of the refracted material. So theta incident is going to be this angle right here. It's the angle from our incident line to our normal line. N incident is going to be the index of refraction of that angle. We can talk about the same thing over on the right-hand side. N refracted is going to be this here, this 2, the index of refraction of the material. Sine of refracted is going to be the angle between, theta refracted is going to be the angle between our light ray and our perpendicular line here. Now remember, the definition that we had for index of refraction had to do with the speed of light. N, which is our index of refraction, is going to be c over v, where c is the speed of light and v is the speed in whatever material we're talking about. Now our c value is the speed of light in a vacuum, specifically, which is 3 times 10 to the 8th meters per second. Divide this by our v, and that's going to give us our index of refraction. Now, one key thing, our index of refraction should always, always, always be greater than 1, or equal to. N has to be greater than or equal to 1. Because, remember, the speed of light, c, is the fastest that anything in the universe can travel. Nothing can travel faster than that. So if our velocity was to get bigger than that, this fraction would become less than 1, which would make n less than 1. So that's not possible. If you end up with an answer, make sure your n value is greater than 1. Last, we have diffraction. Now, remember that diffraction is how waves move through an opening. So if we have a bunch of waves like this, coming in, reaching our opening, we're not going to just see the waves directly in front of this hole, but they're going to spread out a little bit. So our waves may start a little bit confined, but they're going to spread out as they move along, creating this V, sideways V pattern with their spreading out. This is called diffraction. It works with waves moving through any sort of barrier. But the key things that we need you to remember for diffraction are that it is the wavelength and the size of our hole or our slit. These are the two factors that affect how much diffraction we see. If our wavelength is bigger, we're going to see more diffraction. If we have a smaller slit, we also are going to see more diffraction. These phenomena help us understand how, when we're standing next to a doorway or some other opening, we can hear the sound waves as they go through because they'll pass through that small opening and they'll start to spread out. Light doesn't do that quite as easily because of this whole wavelength issue. Light has a much, much smaller wavelength than sound, so it will diffract much less easily. Now remember, when we take diffraction and interference, we get the double slit experiment that we talked about. With the double slit experiment, we had diffraction as the wave moved past those two slits, and then in the areas where there was constructive interference, we had a bright spot. When there was destructive interference, we had a dark spot based on the distances from those two slits. This is going to be the biggest combination that we have of diffraction and interference, and it's actually a pretty important science experiment. So these are all of our notes that we had for kind of the first part of this unit when we were talking about waves generally. There's going to be another video that's going to come out after this that will talk not only about waves, but about the different types of waves, light waves and sound waves, and how they're the same, how they're different, and how we use them in every day.